Now, let us talk about proportionality. All right. Now, for proportionality, we've already in Coulomb's law said that F is directly proportional to the product of the charges, inversely proportional to the square of the distance between them. This same proportionality is going to exist in some other equations. Now, I know this workshop isn't on gravitational fields, but I've included the formulae for gravitational fields because you can see they are actually very, very similar. So that E equals kq over r squared, that's the formula to find the electric field strength if we've got the charge that is creating that particular field. And that G equals gm over r squared is actually the gravitational field, so G represents gravitational acceleration that's caused by a body with mass m. And then that Fg formula you can see is very similar to our F formula for Coulomb's law. Right? So E, the electric field strength, is going to be proportional to the charge that is creating the field, and it's going to be inversely proportional to the square of the distance between the point where we're trying to find the field strength and the thing that's creating the field, which we know. Hey? We know from magnetic fields, electric fields, that sort of thing. The further away we get from it, the weaker the field is going to get. So no surprises there. Right, so for Fg, same as Coulomb's law, now we're just talking about mass rather than the magnitude of the charge. And then for this G, it's going to be similar to that field. The gravitational acceleration on a particular planet, for example, is going to be greater if the mass of the planet is greater. All right, so if you go to Jupiter, you'll probably be squashed by the gravitational force there because it's such a large planet, so much bigger than Earth. All right, and then same thing, inversely proportional to the square of the distance. The further you go away from this large body like a planet, the less and less gravity is going to affect you. So let's see. The force of attraction between two charges is F and the distance between them is R. The magnitude of each charge is doubled and the distance between their centers is tripled. What is the new force of attraction in terms of F? Okay, right, so let's see here. Initially we had F, right? And that was just between the two charges. So I'm going to put here I, right, as in initially. So the force was F, the charges were, I assume, Q1, Q2, and the distance between them R, right? And now we're going to go and double the magnitude of each charge. Okay, so for F, we're going to double the magnitude of each charge. So now we've got 2Q1 and we've got 2Q2, and we are going to triple the distance between their centers. So that's now going to be 3R. Okay, and now we've got to find the new force of attraction in terms of F, that force of attraction that we had originally. Now F is directly proportional to the product of the charges, right? So if we take this 2Q1 times 2Q2, the 2 times 2 gives us 4. So now we get 4Q1 times 4Q2. So if we increase the product of the charges by a magnitude of 4, we've got to increase F by a factor of 4. So 4 times F is the result of doubling the charges, right? But that's not the only thing that happened. We also changed the distance between their centers. Now F is inversely proportional to the square of the distance between the centers, right? So what that then means is whatever we do to R, the inverse of the square of that is going to be done to F. But the easiest way to do it is to use this direct proportion symbol still here, where we can then put the 3R underneath like this, where we then have 1 over 3R squared, and 1 over 3R squared is going to be 1 over 9R squared, which is actually then just the same as the, I'm going to continue down here because I can, the 1 over 9 times the 1 over R squared. So what we've done to this 1 over R squared is we've multiplied it by 1 over 9, and the result is that we're going to get 1 over 9F from it. So tripling the distance between the centers has decreased F by a factor of 9. And now to get the new F, so I'm just going to call it F new, it's going to have to be the 4, right, the increasing by 4 due to the product of the charges times the decreasing by a factor of 9 due to the distance of the previous f, and it's going to be 4 over 9f. Right, so I've separately gone and figured out how does changing the magnitude of the charges affect the proportion, how does changing the square of the distance between them affect the proportion, and I've put that together in order to decide, well, what is this new f going to be in terms of the old f. Let's keep going. So here it says the gravitational acceleration on planet A is g. Planet B has a radius 2/3 the radius of planet A and half the mass. Express the gravitational acceleration on planet B in terms of g. Right, so here we're going to start again with A. Right, so A, we know the gravitational acceleration is g. And here B is 2/3 the radius of A. So for A, I'm just going to call the radius r, and I'm going to call the mass m. Okay, and note here we're dealing with this formula here now, g equals the gm over r squared, where we said that the g is going to be directly proportional to the mass of the planet, and the g is going to be inversely proportional again to the square of the distance between the center of the planet and whatever it is that is experiencing that gravitational acceleration. Right, so for B, we're trying to find out what this g is in terms of the new g, and we know that the radius is 2/3 the radius of m, and the mass is half the mass of m. Okay, so g is directly proportional to m, so if we are going to halve m, right, the effect of changing the mass is going to be that we halve g, right? So this is then going to give us half g due to just changing the mass. But then we've also got to see how does changing the radius affect it. So here we know g is inversely proportional to the square of the distance between it. Now we've got 2 over 3r. So this is 2 over 3r. And then remember that whole thing is still squared, right? So 1 over 2 over 3r squared, we're just going to square top, square bottom. So it's going to be 4 over 9r squared. And this then is the same thing as 1 over r squared times 9 over 4. Okay, so that then is what happens to g due to changing the radius. So the actual effect is going to be the combination of changing the mass and changing the radius. All right, so the new gravitational, let's call it g new, or I guess I could call it gb because we know it's on b, right, is going to be the half times the 9 over 4, so this was due to changing the mass, this was due to changing the radius, times g, and that's going to be 9 over 8g. So a slightly stronger gravitational acceleration on that planet B. Right, so now it is your turn to pause the video and try these two proportionality questions. Okay, so well done on giving that a go. Let's see whether you were on the right track. So it says planet A and B exert a gravitation force of F on each other. Express in terms of F the force between A and B if the mass of A is tripled, right? So we're going to have 3m due to that, and the mass of B is halved, so that's going to be halved m, and the distance between their centers is halved, so that's going to be half r. Okay. So here we can kind of shortcut it and say 3 times a half is going to be 3 over 2 m times m. That should be ma mb. So we know that due to the mass changing, we then have 3 over 2f due to the direct proportion there, right? And then in terms of the 1 over r squared, right, we have 1 over r squared, which actually now became 1 over a half r squared. Okay, with the square outside the brackets, which is 1 over a quarter times r squared, and that then is 4 times the 1 over r squared, right? So halving the distance between these two planets is actually then going to increase the force by a factor of 4. And so to find the new, we simply have to combine the two effects, changing the mass and changing the radius. So 3 over 2 times 4 times f, and that should then be 6f. Okay, So then for the second one, we've got the electric field strength at point X, and that electric field strength at point X is E. The magnitude of the charge that creates the field is doubled. In terms of E, what is the electric field strength at point Y, which is twice as far from the charge as point X is? Okay, so we know again that E is directly proportional to the charge of the thing that's creating the field, right? And we know that E is inversely proportional to the square of the distance between the thing that's creating the field and the point where we're trying to find the electric field strength. Right, so if we are going to double the charge, that's going to be 2Q, and that's then going to give us 2E as a result, right? And if Y is twice as far from the point as X is, that means we've actually doubled R as well. So this is going to be 1 over 2R, which we're going to have to square, which is going to give us 1 over 4R squared, right? Which is then the same as the quarter R squared. Right, and that's going to mean that we're going to go a quarter E. This is still 1 over R squared. Okay, quarter E. Right, so changing the charge, doubled E, doubling the distance, divided E by a factor of 4. So if we combine the two things, the new E is going to be the 2 times the 1 over 4 times E, which is going to be a half E. Fantastic. Right. So well done if you got that correct. Let's keep going. Right.